Alright, so hello madam. I hope you're having a really good day. Me and my group member are going to talk about our presentation, which is the topic is topic 3. We chose the subtopic are best fit and worst fit. The reason why we chose this because we find it really understanding and it's really quite easy to understand. So hopefully the way we do it, it's acceptable. I'm going to present my first presentation where I choose best fit. So I think let's begin it right now. So what is best fit, you may ask, madam? Method of allocating memory to the processes at runtime. The idea is to divide the available memory into a number of equal sized partitions and then allocate partition to a process when it requires memory. The algorithm used to determine which partition to allocate the process is known as a replacement algorithm. Best fit is a placement algorithm that tries to the smallest partition that is large enough to accommodate the process. To do this, the algorithm maintains a list of all available partitions sorted by size. When a process requests memory, the algorithm searches the list for a small partition that is large enough to hold the processes and allocates the partition to the process. Let's say, for example, this table right here, you can see down there. Suppose we had the following list of available partitions, right? So in this table we have, as you can see, the table below there, we have 4 partitions, P1, P2, P3, P4, and the size is quite not that big, quite small, quite medium. So we have the first partition is with a size of 25 KB, the second partition 50 KB, the third partition 100 KB, and the last one, which is P4, that stands up with 48 KB. So how am I going to solve this? Yes, by using this scheme, right, to make sure does it fit, does the size fit, right? So as you can see, you might be asking yourself, what is U and H, right? So U stands for use and H stands for whole, right? So why whole? Why whole, right? In this term, whole means is a space where it has more space that can be stored with more data, while meanwhile the letter U means it's use, so we cannot use the box use because it's in the name, it's use. So how on earth are we going to fit the right H, the right hole, right? So that's the calculation begins. So let's start with the first P1, which is 25, right? So where should we put the data in the right belonging of whole, right? So we look at the range between 10 and 40, right? It seems suitable. When you minus it, it becomes 30, right? 30 space right there, you can see it. So yes, it's 30. Let's look at another whole, which is really close, right, to 25. Let's just say 123, between 123 and 200. It's 77 space. It's good, but right now we're looking for the best fit, right? It means that we have to look for the data that fit inside the hole. Not when you fit inside the hole, it's still more space. What's the meaning of best fit? Am I right? I think so. Let's look another hole, like between 379 and 460. I mean, it fits. It really does. But unfortunately, if we put data, it still fits, right? So now the best hole to use store data for P1, which is the space between 10 and 40, equals 30. So P1 is the size of 25 with minus 30, and of course the balance will be 5. That's easy, simple, right? And then we must update the data, numbers of data in a scheme. So again, as you can see from the picture, is 10 to 35 to 40. See? And then start for P2. P2 with a size of 50 kilobyte. So right now, let's do it again. Let's search which hole is going suitable for P2. And again, we can't use the hole between 10 or 40 because we already use it. Once you use it, we will minus it from the first data, which is only limited to 5 balance. 5, it means only 5 data can be stored. So 50, where is the amount of balance that is so close to 50? The answer is between 123 and 200, with the balance of 77. So it's close enough, and that's what you get for P2. Yeah, P2, 77 minus 50, and you got 27. And it's 27 more balance. It means you can store more 27. And again, we have to update the numbers of data. So it's, as you can see again, it's 123 and become 175 to 200. Let's see for part 3. Part 3, yeah, we have to take the range from 460 to 379, right? So we minus it first. Sorry, 460 to 179, right? So we take it and then we minus it and see there's 181 space, right? So P3 is already underneath our nose that this is the closest where the P3 could get, because the size of it's 100 kilobyte. So it's easy right there. 181 minus 100, and you get 81 more balance for data. And again, you have to update the data and under the scheme, you can see right there 279. And the last part, the version 4 with a size of 48. And again, you can choose the hole from P01 or P2, right? Because the number is 48. So there's no other place that is so close to 48, but there is some one hole left, right? Which is with a balance of 81. So we have to do it. That's the only place that's that be able to store data. So 48 minus 81, sorry, 81 minus 48, and as there you can see, you get 33. And the last update data, you can see it there, is 427. So yeah, that's all for me, madam. I hope I explained it clearly. And yeah, thank you for listening to my presentation. And now you're going to listen to Hari. Thank you, madam. Appreciate your time.
Hello, I'm Hari Prashant Raj Rajendran, and I'm going to be your fellow presenter for this OS project today. So I'm pretty sure my partner, fellow presenter, have presented his part before. Now I'm going to present my part. Okay, in the world's fit dynamic partitioning algorithm, the operating system looks for the largest available hole in memory to place the incoming process. So what is the idea behind this approach? Okay, so the idea behind this approach is that since the hole is so large, it is less likely that the system will need to perform another memory allocation in the near future. So what are the examples of how the worst fit algorithm that might work? So here's an example. There's 3 examples. First, we have the operating system receives a request to allocate memory for a new process. Yeah. And the second one we have, it scans the list of available holes in memory and selects the largest one. Yeah. Third, we have it places the process in the selected hole and updates the list of available holes to reflect the change in memory allocation. So there we go. There were the examples of how the worst fit algorithm might work. So now let's look at another example of a table. Okay, so we have 3 rows and, my bad, 3 columns and 2 rows. First up, we have hole 1, hole 2, and hole 3. As you can see in hole 1, we have 20 units of memory. In hole 2, we have 50 units of memory, and in whole tree, we have 10 units of memory. So yeah, that was the following list of available holes in the memory. Next up, we have this. If a process arrives that requires 30 units of memory, the worst fit algorithm would place it in hole 2, resulting in the following list of available holes. Yeah. Okay, so the same as before, the thing that changed right now is in hole 1, as usual, we have 20 units of memory, but in hole 2, there's nothing because that's where the worst fit algorithm got placed. And in hole 3, we have 10 units of memory. So that's how basically this thing works. So the worst fit algorithm has the advantage of potentially minimizing the number of times the system needs to perform memory allocation, since it's trying to find the largest possible hole to place the incoming process, as we talked in the beginning. However, it can also lead to inefficient use of memory, as the system may end up with many small holes that cannot be used by any process. So yeah, thank you for listening, and that's my part.